objectives for this lab were to construct a motor using the given materials, use said motor to test the variable and non-variable properties that affect the speed of the motor, and ultimately design an experiment that will use the properties discovered to create a faster revolving motor. For our setup, a looped wire was placed over a stack of magnets and connected to several batteries. One end of the looped wire was completely sanded, while the other end was only half sanded. In order to test the properties that affect the speed of the motor, we placed several different amounts of batteries underneath. From our trials, we hypothesized that the more batteries placed underneath, the faster the motor spins. While both sanded sides of the wire touch the metal rod, the circuit is completed as seen on the left and current can freely move through the wire. However, when only one sanded side is facing downward, the current cannot move through the wire, as the circuit is broken as seen on the right. While current is actively moving through the wire, it interacts with the magnetic field created by the dipole and the magnet below. The magnetic field lines in the magnet protrude from the north end and point toward the south. Using Fleming's right-hand rule, a more completed model of the motor can be constructed. The magnetic field, current, and the direction of the force are all perpendicular as demonstrated by the diagram. Taking all of this into consideration, we can begin to understand how the motor works. When a current is active, it loops through the wire, interacting with the magnetic field coming up from the battery. This creates a magnetic force inward on the top wire and a magnetic force outward on the bottom wire. When the current is inactive, a magnetic force no longer acts on the wire. However, the momentum carried as a kinetic force along with the force of gravity on the side moving downward are able to overcome the force of gravity on the side moving upward, flipping the ring over and reconnecting the circuit.
The revolutions per second were found by counting the amount of rotations in 10 seconds after the video was put in iMovie and slowed down to a countable rate. We found that 1.5 volts produced 2 revolutions per second, 3 volts produced 1.8 revolutions per second, 4.5 produced 2.1 RPS, and 6 volts produced 2.6 RPS. All this data makes sense except for the first point. We would expect the lowest volts to produce the lowest RPS, but this may be due to the fact that the first one had to be spun by hand to get the loop spinning. This graph shows that as volts increase, RPS should increase, and we would expect this graph to be fairly linear, which it is, and the only outlier for this is the first point, which we explained was because it was spun by hand.
The results of our experiment proved that our hypothesis that more batteries spins the motor faster was correct. This can be attributed to the magnetic force equation. Magnetic force is what ultimately caused the wire to rotate and is equal to the cross product of the current times wire length and magnetic field. The current is equivalent to voltage over resistance, and since resistance, length of the wire, and magnetic field are constant in this scenario, an increase in voltage via batteries increases the speed of the rotation. This mechanism is similar to the ones found in DC motors of common toys, with the exception being that these motors reverse the current once the wire flips over, instead of breaking the circuit altogether.